Hello, welcome to the presentation on the topic Visual Positioning of the Drone in Condition of Impossibility of Using External Navigation Signals. Our team brings together specialists from the National Aerospace University, Kharkiv Aviation Institute, who work together to develop the latest navigation methods. Each member of our team makes a valuable contribution to the research, providing a comprehensive approach to data analysis, development of new methods, and implementation of results in scientific and practical activities. My name is Oleksii Hurtovyi. I am a PhD student and developer. Kostiantyn Dergachov, head of research and main advisor. Anatolii Yaremenko, a research and data analyst. Our research focused on developing a visual navigation algorithm for drones. It allows autonomously determining the coordinates of objects using a camera, which is important in environment without an external signals. The research used Python, NumPy, and OpenCV to implement process and data processing. This slide presents a list of references to publication in the field of visual navigation research and its methods over the past few years. In the process of analyzing the sources reviewed, and significant attention was paid to such aspects as accuracy of calculation, autonomy, adaptability of the system, and its easy integration. The development of visual navigation methods without using GPS has become critically important in many industries. In robotics, a key problem is the accuracy of determining the coordinates of objects, which often depends on lighting conditions. SLAM and GIS methods have limitations due to high computational complexity and dependence on maps. In our research, we paid attention to visual navigation technologies using camera. They allow to work autonomously even in environments without a GPS signal. Also, they remain sensitive to lighting, weather, and sensor noise. However, with the help of adaptive algorithms, the accuracy of calculation using this approach can be significantly improved. The presented algorithm consists of 5 main functions. The first provides the capability to detect green object in space using the HSV image and certain kernel parameters. The algorithm filters the image, finding the necessary contours. The second function is rectangle processing, which calculates the geometric parameters of the objects, such as center of mass, height, width, its rotation angle, and others. This data is the basis for the next stage, determining the distance to the object. The fourth function is sign calculation, where the algorithm takes into account the rotation angle of the drone, which is an important component of the final functions, which serves to accurately determine the spatial coordinates x and y. Each function is integrated into a general algorithm that ensures the autonomy of the drone. Each stage of system implementation requires additional control of parameters, boundary ranges, as well as filtering of noise and unnecessary elements, in order to more effectively identify the object in the frame. Therefore, morphological operations are applied to the contours, and a special range is selected for object detections, which is optimal for the tasks of detect several objects around the drone. Based on the initialization of the camera parameters, as well as the dynamic change in the pixel value of the target object, the distance to it is determined during the flight. Moreover, the work is carried out precisely with the center of mass of the detected object, since its height may be inaccurate due to reflections on the surface being hidden or covered by another object, as well as due to poor lighting, shadows, or perspective distortions caused by the camera angle. This ensures stability in tracking the position of the object on the plane and its subsequent finding on that coordinate, which is the basis for visual navigation in unknown space. The algorithm consists of three stages: object identification through color masks, calculation of the distance to the object based on the dimensions and camera parameters, and calculation of x and y coordinates using trigonometry. The equations presented on the slide show the procedure for finding the coordinates of a detected object. After data processing, the rotation angle is calculated and the distance is found. Hence, the x and y coordinates are found by solving a problem with triangle in space, where one of the sides is determined by the sine of the angle and other by calculation the hypotenuse. The algorithm was adapted to work with DJI Telo-edu drone, which has a basic set of functions for programming. Using Python together with OpenCV and NumPy libraries ensures quick integration and scaling of the algorithm. This approach makes it easier to adapt the development to different hardware platforms, even with limited resources. When working on the problem, various situations that happened when calculating the final coordinates were taken into account. Among them, the features of the equipment and their power, inversion and assignment of coordinates and others. The algorithm is autonomous, works in real time, doesn't require expensive sensors, and can work regardless of magnetic interference. However, the efficiency depends on lighting, and the camera has a limited range and doesn't provide data on that coordinates. Testing the algorithm on a DJI Telo-edu drone show high efficiency. However, to increase accuracy, higher quality cameras and more powerful computing components are required. The uniqueness of the method is the use of trigonometry, which is also relevant when searching for the Z coordinate in visual navigation methods. This opens up opportunities for working in three-dimensional space. To assess the accuracy of the algorithm, a comparison of programmatically calculated coordinates with real measurements was conducted. Based on obtained data, additional software components and models were created that allow the algorithm to be universally scaled depending on the tasks. For example, if it's necessary to process data from a larger number of objects or add prediction functions, the algorithm is easily adaptable. The method errors were also assessed and additional parameters were calculated, including averaged values of the obtained coordinates, total square deviation, and others. The prospects of this research are integration with neural networks, project with 3D spatial synchronization, and the creation of new algorithm for low-power devices. Application is possible in such areas as the development of drones, robots, rescue or military operation, medicine, smart logistics, the agricultural sector, and others. This will expand the functionality of drones and make them indispensable in many areas. Future research is to find the Z coordinate of an object captured from a camera, calculation of the UAV position in unknown space, software development, and comparison of visual navigation methods. The algorithm provides autonomous drone navigation without GPS, supports to accurately determine the coordinates of objects, and is easily integrated into various platforms. Thank you for your attention.